So let's do section 5.4, and we're going to be looking at enthalpy again. And remember that the delta H is change, delta is always change in enthalpy. Well, now they're going to throw another symbol at you, and it's very similar. You've got delta H, but they're going to put a little degree sign up here and an F down here. That's the delta H of formation. So what that means is that we are going from base parts to 1 mole. Alright, so what I'm talking about by there is if I have NH3 ammonia gas, okay, and it should always be in its standard state, whether that's solid, liquid, or gas. Ammonia's standard state happens to be a gas, but its individual parts are the nitrogen and the hydrogen. So we'd say N2 gas and H2 gas. Okay, and then we'd say, okay, I only want one of these, 1 mole of it. So that I only have 1 mole, I need half of this and 3 halves of this. Right, so that this 1 corresponds with that 1, and this 3 corresponds with that 3. If it is a gas, it is also at 1 atmosphere. If it is a liquid or a solid, it should be pure. If it cannot be pure, it should be 1 molar. Okay, so that's also what those two symbols mean. Okay, now you have a ratio of 1 mole to its base parts. If it's a gas, to 1 atmosphere. If it's a liquid or a solid, it's pure, or it has a concentration of 1 molar. All right, the delta H of formation for any individual thing, so for H2O or any elemental thing, is 0 joules. Okay, now we can take this and we can use this formula. And I'll explain what it means here. So this right here means the sum of, and we know the moles, and that P of product times the enthalpy of the product. Alright, and then we would subtract that from the sum again, sum of the moles reactant times the enthalpy of the reactant. Alright, so let's look on page 274 and use this, or 49, I don't know where I got that, sorry, 249. It says, using the standard enthalpies of formation, which is that delta HF, not F, listed in table 6.2, calculate the standard enthalpy change for the overall reaction that occurs when ammonia is burned in air to form nitrogen dioxide and water. Okay, so we are going to say we have 4 NH3 plus 7O2 going to 4 NO2 plus 6 H2O. The book goes into a lot more detail about why this works and everything like that. Talks about the decomposition, where everything comes from, but I'm just going to plug it into that formula that we just saw. So the first thing it said was the sum of all the products. Well, these are all of my products. Okay, so I'm going to do those two things. And I'm going to go for sum of the moles of the delta H naught of my product, and for, sorry, I'm looking at my notes here, for NO2 that should be 34 kilojoules. Okay, and then my second product has 6 moles and water is negative 286 kilojoules. Alright, so the sum of these two products, so I'm adding them together with their moles, or their molar ratio, times their enthalpy, minus the sum of my reactants, those are my reactants, with their molar ratio times their enthalpies. So for NH3 it is negative 46, 7 molar ratio, and because this is O2 it is 0. Okay, so we add that all together and we get a negative 1396 kilojoules is the delta H for that reaction, the enthalpy change, the heat flow for that reaction. Alright, let's do one more and see if it helps clarify a little bit. On page 251, it says, using enthalpies of formation, calculate the standard change in enthalpy for the thermite reaction. A lot of you guys know the thermite reaction. It's fairly fun to watch. 2 aluminum plus iron oxide going to aluminum oxide plus iron. This reaction occurs when a mixture of powdered aluminum and iron 3 oxide is ignited with a magnesium fuse. So we write down our equation. 2 aluminum plus iron oxide going to aluminum oxide plus iron. Alright, so first we look at our, products minus reactants, the sum of those, and so we have 1 aluminum oxide and it has a delta H of 1676 plus 1 of my iron, and since that's elemental it will be 0, minus my reactants, so that's 2, and aluminum is elemental, so it'll be 0, plus 1, and iron oxide is 826. So this equals an overall enthalpy of negative 850 kilojoules.